Thanks, Kate. You just did what you've been doing so well during the whole meeting. I'd also like to thank Jim Babb. Any technical difficulties with this talk are down to my ignorance, not to his lack of helping me. Hussein also deserves our thanks, and I want to thank all three of you for including me on the program. Now, I was very pleased that the similarity between James Bond and Alex Dalgarno was brought up earlier today. Alex has won so many medals that his stock of precious metals at home, well, in various bank vaults, would be sufficient to undermine Goldfinger's plan to irradiate Fort Knox. I had the good fortune of being at two of the award presentations. One was the gold medal of the Royal Astronomical Society, which I believe was in the mid to late 80s, and the Hughes medal of the Royal Society, which was about 4 years ago or so, 4 or 5 years ago. And if you bother to look at the list of distinguished recipients, you will get some idea of how special Alex, how special the recognition Alex has received, that he has those two, and those are just two of very many. Now, I noticed John Black's comment about Leo Goldberg's advice. I had the good fortune of meeting Leo. The first time I met Leo, it was in the presence of Alex, and I thanked him for hiring Alex to come to the States. But I'd like to turn to the advice that Leo gave John. The first piece of advice he took, which was to study with Alex. The other one was to focus on one area. Now, we've all heard of what a huge diversity of problems on which Alex has worked. And I would have to say that Alex is a visionary system builder driven by curiosity. Now, John was told by Leo Goldberg to focus, and in one way you could say that Alex has not taken that sort of advice by being so diverse. I, on the other hand, hold Alex up as an example to students and postdocs and other young people to show them how a very fundamental sound basis in a particular area can be exploited to grow and systematically and methodically build and widen over the years. Alex has done a lot of different types of problems, but there have not been wild, uninformed leaps from area to area. What Alex has done is he's had a vision, sometimes 15 years or even more in advance. He says, I'm going into a certain direction, and I'm going to learn how to do that, and I'm going to relate it to what I already know. So I think that is the way I've noticed other great scientists have operated as well. I hope you agree with that analysis, that that's the way you work, or am I totally wrong? Okay, he agrees with some of it. That's just about the best I ever get out of him. Now, last night I promised to tell you something about the intellectual support that he provided for me. I came here interested not solely in molecules. I developed quite early on an interest in dynamics, which Alex encouraged and was very supportive of. And just as one example, one of the problems that I became interested in because of things I was learning from Alex was cosmic rays creating ionization in interstellar clouds. And one of the things that dawned on me is that alphane waves may in fact prevent cosmic rays from entering freely into interstellar clouds. So at that time I set about trying to learn the appropriate cosmic ray physics. Alex was very supportive of that, and he let me go off to Cambridge for 2 summers, not to do cosmic ray physics, but in the second summer that I was there in 1977, I received a letter from him. These are pre-email days, and he said, take a look at the most recent Astronomy and Astrophysics, and you'll see that John Skilling and Andrew Strong, who've done the problem that you were suggesting, and they knew enough to do it. Now, I think this is a really great reflection on Alex. He was interested enough in supporting me in my idea, even though I was a young graduate student, that he directed me towards something in the literature. And we, in fact, used that paper in some work that we later did together that related molecular observations to cosmic ray physics. The other thing that I think that particular story reveals or provides a good example of is the fact that Alex, pre-internet days, pre-electronic database days, had an encyclopedic knowledge of an incredible breadth of literature. It wasn't just a question of remembering roughly what year something was published or that. He could tell you almost down to the month, sometimes even to the page number, where to find something on some subject that was very distant from what you might have expected him to be thinking about that day. Okay, the last thing I want to comment before I get into the normal part of the talk is that I was very pleased to hear some of the history about ITAMP yesterday. I'm an astrophysicist, not an atomic physicist. I promised ITAMP and NSF that I never received a penny from ITAMP while I was here to do theoretical astrophysics work, but on the other hand, I did have the good company of people working in ITAMP, so I think they're morally clean on that, as am I. But I remember when Alex was drafting the first proposal, and I had the privilege of reading it perhaps shortly after it was submitted, one of the lines in it which made a tremendous impression on me concerned the fact that the physics is in the solution of the equations. And of course, this is 20 years ago, but as I've matured as a scientist, I've become to appreciate that insight more and more. Okay, so enough of all that. I have another question for Alex. And I'm the third person to refer to this 1986 paper. I think David Williams helped you come up with the title. Is that right? Or not? Don't think so. Okay. Okay, my question for you is, given that in that particular paper, I think that you were trying to encourage the community to do the job of making chemistry useful, you were encouraging us seriously to attack that problem. Do you think it is useful? Okay, yes, good. I can give the rest of my talk. I thought I was going to get to sit down there for a second. Alex says his mind has been changed. Okay. All right, well, the paper was in 1986, but even predating that paper, Alex stressed several basic aspects of astrochemistry. That was, and I'm not quite sure when you formulated these. You certainly were saying them by the mid-'70s when I first was beginning to study with you. That the chemistry can have diagnostic utility, that chemistry influences the astrophysical environments in which the chemistry occurs, and that the chemistry or molecular astrophysics involves a large number of physical and chemical processes which are of interest in their own right to physicists and chemists and a lot of other types of scientists. So, in fact, this talk is going to be based around those three aspects of astrochemistry. And what I'm going to do is, in each of those three areas, I'm first going to say a few things about some of Alex's important contributions. There isn't time to mention them all. And I will say some things about more recent contributions by other people. Now, of course, this is just, there are lots of things I'm leaving out, There are lots of things that I could put in, and my apologies to Alex for leaving out some of his good work, and apologies to a lot of the other people in the room for leaving out some of their good work. You'll notice that there'll be a reasonable overlap between what I say and what Evine said the other day in terms of what we're pointing out as highlights. I hope that those parts that are repetitive reinforce these points in your mind, and those parts which are different show you that the field is so rich that one can view it differently depending on one's perspective. Okay, so let's start off with selections of Alex's contributions to astrophysical diagnosis. Well, Evine mentioned the Black and Dalgarno 1977 paper, which dealt with the Zeta Ophiuchi cloud. This is a diffuse cloud, which means that it has an optical depth that's in the continuum that's sufficient for about half of the optical light to get through. These things have about half of their hydrogen in molecular hydrogen, half of it's in atoms. Observations with Copernicus of the hydrogen atoms, the H2 rotational populations of the lowest vibrational state at HD, and OH then were used by Black and Dalgarno to infer for this particular cloud the UV intensity, the ionization rate induced by cosmic rays, then the elemental deuterium abundance. They also inferred information about the density and temperature structure. So this was the first of, well, not even the first, but it was one of the key papers in a number of papers which Alex wrote with John and other collaborators. Now, this work was underpinned by a large body of Alex's work on processes, and I'll come back to that later. Now, I mentioned Alex being visionary. My reading of this story is that basically in the 60s, he realized that he and his collaborators would be able to calculate all of the data that were necessary to carry out this program, and because of that, he was able to conceive the program. And I suspect that because of his ability to calculate all of the data, that he was probably the only person capable of conceiving that program at that time. Okay, I'm just mentioning a few of the other papers that were involved in this. The Black and Dalgarno 73 paper I listed again under investigations into processes, but it concerned the cosmic abundance of deuterium. Dalgarno Black and Weisheit orthopara transitions in H2 were relevant to this cosmic ray ionization of deuterium abundance. This was a paper in which I was fortunate enough to be involved. Okay, so that's diffuse clouds. I'm not going to talk much about the solar system because that was in other people's remits, but this is a very special set of papers that Alex wrote in the mid-90s dealing with the Jovian day glow. There are some overlaps in the approach on this. This is partly an energy deposition problem. The cosmic ray induced ionization in the interstellar medium is an energy deposition problem as well. So there's a commonality of techniques, maybe in techniques and underlying approach, though details are somewhat different. But Alex was able to show that there's a presence of large temperature gradients in the Jovian atmosphere from the analysis of these observations. So this is still diagnostic. Okay, well, turning to denser interstellar clouds, I believe Evine may have mentioned this one as well, but the deuterium fractionation in denser molecular clouds. These are things that you can't see through. You have to use millimeter wave and infrared observations to probe. And these are the sorts of things where stars really form. And you have to get a handle on what the ionization in them is using a different approach than you do for diffuse clouds. And Alex and Steve worked on that, and one of the things that they addressed was the fact that I think Steve mentioned this as well the other day, is that a lot of the deuterium is actually in atomic form, even in these dense regions, rather than all of it being tied up in HD, as other people assumed in their analysis. This was very important for looking at cosmic ray ionization rates. Now, cosmic ray ionization rates are particularly important in these regions because the cosmic ray induced ionization affects the way the magnetic fields behave, and magnetic fields regulate star formation. They're particularly important in angular momentum transport. They can slow star formation down and affect the way things fragment. Okay, moving out of the interstellar medium into supernovae. I'm going to come back to supernovae later, but who would have ever thought that molecules could be used to study the explosion process in supernovae? Well, by considering the chemistry that gave rise to the formation of carbon monoxide in supernova 1987A and to its destruction, Alex and his collaborators were able to infer that even though there are Rayleigh-Taylor instabilities occurring in the explosions, that the microscopic mixing between regions of different layers of different nuclear ash, the microscopic mixing had to be extremely limited. So even though there were big macroscopic deformations of the interfaces between these different regions, those big deformations did not lead to any microscopic mixing. I think this is an absolutely amazing result. So there's the giant, and then there's the rest of us here. Okay, some of the things going on. Aveen mentioned this the other day. H3 plus has been observed and has been used as a diagnostic of the cosmic ray ionization rate in diffuse clouds. And the cosmic ray rates are an order of magnitude higher than people used to guess. There were some indications of, even in the 70s, of some regions with high ionization rates. But this has been a very useful diagnostic. Okay, in the dense cloud work, Caselli and her collaborators, not so recently, but they didn't contribute any new conceptual ideas, but they have exploited the framework laid by Alex and others for diagnosing the ionization rate, the cosmic ray ionization rate. Okay, this is just a very handful to give the flavor of the way the field is going now. All right. For a very, very long time, people did not have a definitive signature that any region was actually collapsing to form stars, except that stars are there. But if you go out and look at the molecular lines and try to look for signatures in their profiles of collapse, it's very difficult to find them. It involves, okay, so people have risen to the challenge of this difficulty, and they're now coupling dynamical models, chemical models, and radiative transfer models all together to try to interpret observations, and not just from one line, but from many lines from many, many different species. Okay, this is a very ambitious task, and I've picked one of the recent excellent papers in that area. Now, Aveen mentioned that more and more focus is going to go into the dynamics of disks, particularly with ALMA coming along. And she mentioned a more recent paper on organic molecules and protoplanetary disks. But of course, as ever, Aveen was pretty far ahead in the game, and she was studying organic molecules even when not all of the observational tools were there to use. And of course, there's been theoretical work which is preparing for that as well. There's lots of work to be done in this area, but these are valiant initial steps in a very important problem. Well, chemical and quantum control of astrophysics, some of Alex's contributions. Pat, I'm sorry I didn't look. How much time do I have? 20 minutes, 25 minutes, okay. Great. I'm glad Pat mentioned this. I think it's been mentioned in other talks as well, but the important work that Alex has done with Steve Lepp on the heating of the interstellar medium by large grains, and large molecules and small grains. And this is where you find that molecules can carry both positive and negative charge. I was very pleased to hear about Pat's line identification work in this area. I neglected to mention it later on when I was talking about important work on processes, but I'm glad he mentioned it now, because then that way I'm able to reinforce the importance of that work. Okay, well, of course, Alex got into the heating and cooling game a long time before the 1988 paper, and the Dalgarno and McRae paper, you know, is a very important one on heating and ionization of the interstellar medium. Now, something that even the astrophysicists in the room may not be very aware of is that Alex played a very leading role in helping people realize that the interstellar medium, even in the days when people were thinking of two-phase models, could not be in equilibrium. In 1970, he published a paper with a number of co-authors listed there, in which he included the effects, the time-varying effects of supernovae on the ultraviolet background, also the lifetimes of O-stars, I believe, and argued that there isn't time for a two-phase medium to come into equilibrium. So, of course, a few years after that, other people started looking at supernova effects on the interstellar medium. They started to include some of the effects of the mass injection and the energy put in that way. But, you know, if you were to believe that the supernova remnants don't fill a very large volume factor, in fact, there are a number of people who do that, then actually you get back to the point where this sort of model is actually a reasonable way of looking at a lot of the interstellar medium. There are no molecules there, but this paper's always been a personal favorite of mine, and I think Alex one time said I was about the only person who ever referenced it, but I've always liked it. Okay, we've heard about the chemistry of the early universe, the role that HD has as a coolant. Well, Alex has contributed in that area. I was talking before about trying to diagnose the fractional ionization in interstellar clouds, but Alex, with Mike Oppenheimer, were the chaps who actually told us what establishes the ionization balance in dense interstellar clouds. It's a very important paper. Okay, well, as I said, Alex was supportive of my interest in dynamics, and as I said, in 1970, he was already pointing out that things weren't in equilibrium. He got into the interstellar shock game in a big way, partly while I was a graduate student, but from the control aspects rather than the diagnostic aspects, Alex has contributed in a very major way by making sure that the community knew what data should be used while making modeling. And he got together with Bruce Drain and Wayne Roberge, and that particular paper has a compilation of data which everybody who's modeled interstellar shocks has used. And it's not just to use it for diagnostic purposes. The data that are in that paper are extremely important for actually calculating the dynamical structures of these shocks. Partly from the cooling, partly from establishing the ionization balance, and everything. Well, we're back to supernovae again. Okay, before I mentioned the CO as a diagnostic, but the studies that Alex performed on supernova ejecta were not confined to just diagnostic studies. In fact, you can't really do the diagnostic studies thoroughly unless you understand the heating and cooling. To understand the heating and cooling, then it's an energy deposition problem again. And by making these very detailed, successful models of the thermal structure of the supernova ejecta, this is supernova ejecta days, like 110, 130 days into the evolution, Alex was able to explain the large inhomogeneities in the thermal structure of supernova 1987A's ejecta as being a consequence of the variation of chemical structure throughout the oxygen core. Okay, now it's the giant and the rest of us again. I'm sure Alex will be amused to see the name Telemachus muscovius up there. You didn't know that he's an astrochemist. But Telemachus has actually been one of the people who's been most careful in trying to get the ionization balance right when making models of the evolution of interstellar clouds. And he's included a distribution of different grains in these regions. It turns out that it's another case where particles, nanoparticles, can wind up being important charge carriers, negative charge carriers. And they contribute a lot of the drag, a lot of the coupling between the magnetic field and the neutral gas. And I have to say that Telemachus is pretty careful about chemical control. I do similar work in interstellar shocks. I'm going to toot my own horn here. Everybody thinks that the problem of C-type shocks was solved a long time ago. In fact, the approximations were good for a lot of interesting parameter regime, but when you go to very dense regions, it turns out that you have to treat the grains differently than people treated before. And it's the point where some people didn't, well, until very recently, people were not including all components of the current and missed lots of effects. Well, we're finally at the point where we're going to rectify some of that in studying oblique shocks, and we'll treat the charge balance and charge and grains in a way that's roughly as sophisticated as Muscovius does in his lower temperature calculations. So there's nothing conceptually new there, but it's an application of astrochemistry to important dynamical problems. Okay, well, a lot of astrochemists think about star formation. There's an awful lot of chemistry going on in stellar death as well. When a star evolves and becomes red, it cools enough so that dust grains can form. Even before the dust grains form, simple molecules form. And it turns out that the radiation pressure on these simple molecules and on the dust helps power the winds of these stars. Now, a star, an AGB star, this is something that has a carbon core and helium and hydrogen burning are going on. It's something that's puffed up with a radius comparable to that of the Earth's orbit around the sun. These things can wind up losing 10 to the minus 5, even 10 to the minus 4 solar masses in a year. That's when they start entering the planetary nebula phase. And dust has a lot to do with that, and the chemistry forms the dust. Now, the state of work in this area is that we're pretty good at making soot on Earth, which we know to our environmental hazard. We're not so good at burning sand. So there's stars that are carbon-rich, and we think we understand how the dust forms there. In fact, one of the people who made the most important contribution in that was a combustion chemist at Penn State, Ficklin, I think. Ficklin, yeah. But the metal-rich stars is another story. And okay, well, these people have been very brave and have made the best guesses for what might be happening in the metal-rich stars as well, and they've tried to figure out how all types of AGB stars return mass to the interstellar medium. But the chemistry of dust formation is very important there. Okay, well, now getting to the investigations of processes, I started off with the study of the diffuse interstellar clouds. Here are a number of papers that are related to the studies of the diffuse interstellar clouds. You've seen these referenced earlier. I'd like to just mention one thing here, and this is Kate Kirby being involved in that. Now, Kate's has very unselfishly given everybody else an opportunity to talk about how they've worked with Alex, but Kate, when I arrived here, was already a very valuable scientific contributor in the group, not just in these problems with interstellar medium, but just on processes and also on atmospheric physics. Okay, well, that's the paper I mentioned before. This is the realization that the way that you couple ortho and para levels is a proton, a proton interacting with H2, and then so you have an exchange reaction. It turns out that D plus reacting with H2 gives rise to HD plus H plus, so it's related reactions. Okay, well, the rotational excitation of molecules, Bala mentioned some things, recent developments that he's involved in on H2 collisional excitation and de-excitation. But Alex has played a major role in calculating cooling rates. A very important piece of work by Alex and Wayne Roberge was a study of how dissociation occurs in H2 and CO molecules. Okay, well, H2 has no dipole moment, means its radiative transitions are slow, so you don't have to go to a very high density to get internal degrees of freedom thermalized. So if you have a warm gas, you can populate high vibrational levels. You can directly dissociate out of a high vibrational level. However, if you go to very low densities, even with H2, then the radiative transitions win. Everything stays down in low states, and so you have to have direct dissociation from a lowly excited state. This changed the dissociation rates. These considerations show that the dissociation rates being used up to that time were great overestimates for low-density regions, and that they, in particular, that direct collisional dissociation of molecules with big dipole moments like H2O would not occur. And of course, these sorts of considerations saw a lot of application in the work that Alex did with David Neufeld. Well, people mentioned charge transfer a lot at the meeting, and you can see there I've got a long, lengthy explanation for why I'm not saying more about it. But I think Alex started working on charge transfer in the 50s, doing Landau-Zener calculations. And in the late 70s and 80s, he really took the problem on in a very serious way quantum mechanically and made some very fundamental insights into when to use diabatic descriptions and things. Okay, so he produced a lot of charge transfer calculations which were incorporated almost immediately in the ionization type codes that people like Gary Furland have, like Patrick Harrington was using. He was working with the UCL group a lot. I'm sure that John Raymond, who's in the audience, incorporated these in his shock codes absolutely immediately. These papers created a revolution in the way people treated regions that were far too hot to have significant abundance of molecules, but these are collisions that involve more than two atoms, so I consider this molecular astrophysics. Sorry, it involved two atoms. I think I just said more than two atoms, but two atoms. Diatomic to me is already a complicated system. Then, of course, there were some fundamental contributions in the development of approaches to photodissociation calculations, which Aveen undertook and did an incredibly thorough job on. And these photodissociation studies are important for OH, which was one of the diagnostics being used for cosmic ray induced ionization rates. Sorry, my poor brain is getting tired. I'm having to jump between too many subjects here. It's hard to keep up with somebody who touches so many astrophysical objects. Okay, well, back to supernovae, and also, okay, there wasn't any carbon or oxygen in the early universe, but Alex did a lot of calculations as well of radiative association rates in the early universe. But the radiative association rate of C and O and C plus and O was an important, calculating that was an important study for understanding the chemistry of supernovae, like 1987A. Okay, so now collections, some selected contributions from the rest of us. Okay, I've referred again to a solar system, to some solar system work. I don't feel too badly about that since Titan was mentioned in such an interesting way by Tom Cravens the other day. But this is just an example of work on fundamental reactions used, with the Cresseux technique that takes place in France. It's in the solar system literature rather than the extrasolar system literature, but that sort of work is still going on and is relevant to the non-solar system physics. Okay, as I mentioned, I was glad that Pat talked about the need for line identifications and high-precision laboratory spectroscopy. I don't quite remember what the subtitle of the Astrophysical Journal used to be, but I think it was something, a Journal of Astronomy and Spectroscopy. I've been informed by people wiser than I that I've remembered correctly. We need to remember that astrophysics is built on spectroscopy. Unfortunately, too many of my astrophysical colleagues forget that. Okay, so the UCL, of course, was where Alex was initially educated. And there's a strong effort there in Tennyson's group, Jonathan Tennyson's group, in calculating highly accurate line and transition rates for molecules of astronomical interest. He's done a lot on H2O, and that paid off in the publication of a paper to which Aveen also referred. That's water vapor in the atmosphere of a transiting extrasolar planet. We have seen, thanks to this work, the atmosphere of an exoplanet. Okay, line lists are also important in studies of what brown dwarfs should look like, particularly in distinguishing them from planets, and also in the study of the oldest stars that we can find. There's some stars that have metallicities that are 5 orders of magnitude lower than the metallicities in the Sun. And we need line lists of sometimes fairly complicated molecules to study those stars. Okay, I've got about 5 more minutes here, maybe even less. Aveen mentioned the importance of dust surface chemistry. And rather than dwell on about gas phase processes, I am going to mention, as she did, that there's been a great deal of extremely important work on surface chemistry. Eric Harrops and Paolo Caselli in the late 90s, wrote a very important paper where they were trying to make an attempt to deal with the fact that the chemistry that occurs on dust grains in the interstellar medium often occurs by one atom sitting there for a while and then another atom coming and finding it very quickly or slowly. But these are systems, surfaces in which there are only a small number of atoms, reactive atoms. Now, this means, of course, that using rate equations is not appropriate. Rate equations involve only the average numbers of particles on a surface, and if there aren't very many, then statistical fluctuations start to become important. So that work by Eric and Powell initiated a number of efforts, the most recent of which is due to Barcel and Behem, where they've tried to use a moment equation analysis of the master equation. Now, Eric told me the other day that he's in the business at the moment, or some people are in the business of seeing if this particular technique works for systems of with real complexity in them. So the verdict is still out on whether or not this is going to work, but I think this is an important direction in which to do research, and Behem has really pushed it in an admirable way. Now, lots of other groups have been working on surface chemistry. I noticed that the names Collings and McCustra don't figure here. David Williams and, yes, those are all UCL collaborators, wrote an article in which they summarized a lot about the work that was going on in UCL and surface processes. They did try to be indicative of some of the work that was going on elsewhere. Work by McCustra's group, Havin's group does a lot of work in this area. Again, I'm going to not list everybody, but if you want to go, if you don't know anything about this area and you want to start somewhere, I suggest the paper by David Williams and his collaborators in astronomy and geophysics. And of course, photodissorption is one of the processes important for determining the way that grains affect interstellar chemistry. And again, Naveen's group has been playing a major role in looking at the photodissorption of CO ice. That's a problem that Eric has worked on theoretically. I have to say that what little work I've done theoretically in this area, anytime anybody does an experiment, it turns out I was wrong by orders of magnitude, and I didn't even make any arithmetic mistakes. It was all conceptual errors. Okay, well, I mentioned the important role of the formation of dust grains and mass loss from stars. I told you that while it's easy to understand how acetylene-rich regions, which the carbon-rich stars are, how they can form dust grains, because you can walk down the street and see somebody using an acetylene torch. But when you look at metal-rich regions, it's harder. So I've picked two papers here. To be honest, I don't understand either one of these papers. I've looked at them well enough to realize that they're important, but not enough to figure out exactly what they've done. Now, one of the problems in figuring out, I'm trying to be honest to avoid questions, you know. Okay, one of the problems in figuring out how nucleation takes place, of course, is that you have to examine a large range of different configurations of N molecules of a certain species to find which one's the lowest energy. Now, ideally, you do this with an ab initio quantum chemical calculation, but we know how hard that is. So people have to come up with clever techniques for doing this problem that don't involve these ab initio quantum calculations, and this is something that Batt and Ford have tried to do. These are UCL people. And then, of course, there's experimental work on that side as well, and I'm including this paper not only because it's an interesting experimental paper, but because I'm amused by the title, which says, silicates do nucleate in oxygen-rich circumstellar outflows. The fact that they have to be so declarative shows you what a difficult problem it is. Pat, you stood up at exactly the right time. Thank you. Thank you.